shopping like on Fridays or something.
And they have
like a 2-hour.
I guess it's
just like, hey, get.
No, it's not closed, but like only old folks can like go in. It's like older folks.
like more
immunocompromised people
Yeah.
that could like if they got sick.
We stopped there.
Yeah.
Okay, so I'm gonna be watching this, so don't talk smack about me.
You can
still watch it from home.
You was
trying to catch us in something just then.
Well, if I wanted to catch you something, do it.
Oh yeah,
he can hear all y'all.
You're the one with the potty mouth.
I'm not. Don't do me.
Don't
do me, dog. All right. Y'all ready to get started?
Yeah.
I have to, because the lobster the lobster's making me.
All
right.
Back, or you just all separately on this?
It'll make me
vomit if I watch it back, so we're just gonna let it go. I don't even want to see these videos.
I don't
want to see these videos after I make them, so please don't ever play them in front of me.
So wait, was it the little redhead girl?
It don't
matter who
No,
it
I'm
was.
just saying, like.
All right, we're live,
Clive.
We're on the
live stream.
Yes, we are.
Yes, we are live streaming right now.
All
right, so
we're getting
started. You wanted to get started. We're fixing to go now. Come on.
Started.
All right.
Motor
controls. We're gonna go to symbols and diagrams.
I made y'all
a nice little fancy slideshow.
Oh my gosh, slideshows is always where I learn the most.
Cool.
I'm glad.
All right.
So just to like go over.
I'm sure
that most of y'all know like the types of diagrams you would see out in the field. Do y'all, or is that like something new? Is it something new to you, Brianna or Samuel, or?
I'm gonna guess. I was looking at the diagrams in the book.
Right. Okay. So you have a basic understanding of it.
So like
some of the types of diagrams that you might see are functional flow block diagrams. One line, single line diagram. They can be called either one. Circuit diagram, connection or wiring diagram, a schematic dash ladder diagram. They all use different names, like wherever, depending on where you're at.
The ladder diagram would kind of be like the ladder logic you see with the PLC.
Kinda. I'm gonna show you an example. So like a flow block diagram. Basically, it's just like input and output of a control system. So it's not really showing you how to wire anything up. It's just giving you a basic gist of what the system would look like. Cool?
Got it?
Okay.
So
a one-line diagram is mostly used to represent three-phase high-voltage systems, but can be used for low-voltage control systems as well. So that's what it looks like. You see how you have your control switch and then your indicator light saying that your motor's on, but it's still not really showing you how to wire anything up. It's just like a general idea of this is what this system should look like.
All right,
a circuit diagram displays an electrical circuit using either basic images of parts or industry standard symbols. Now this is where you start getting a little bit deeper. You have your switch. There's your indicator light, and when that circuit closes in, you have your 120 volt power source, and then your motor is going to come on. You see how that's all happening there? Okay. So connection and wiring diagrams represent the physical connections and layout of electrical components of the electrical circuit. Now that's where you start getting into this is how you need to wire this up. So Caden, you know how to read these connection and wiring diagrams, so you know what this is. I know this is kind of blurry, but I'm about to show you some more examples. So schematic diagrams are the most common. Like used by electricians. Samuel, you said you might want to get out and do some residential wiring, then that's probably what you would be looking at the most. Ladder diagrams are used to document industrial control logic systems. I don't know why these are so blurry. I guess because I got them off the internet. And here's a cool YouTube video. Like somebody that has never looked at ladder logic would be able to. It's just like a 1 minute YouTube video. So bear with it. It just basically describes like how you can follow a ladder diagram. tell y'all too, if you're interested, this is a cool YouTube video channel to follow. HGL Tech Electric, like they have all kinds of videos that like narrow it down and like make it into like terms like you can understand it if you've never even touched it. You get what I'm saying? So HGL Tech Electric is a pretty good YouTube channel. Like I watched it as like a refresher. So
this is
a simple line ladder diagram.
Okay,
so you see how the start is.
I mean,
the stop is closed, so nothing's going on.
And
I know this is very basic for probably some of y'all. I just wanted to let y'all put y'all's eyes on it, so like you know you're gonna press in the start switch,
and that's gonna
cause your circuit to close in, and your motors are gonna come on.
Now
over here, what do you think this is, Dylan?
These over here.
That says OLs.
Yeah.
All those are closed.
They're
normally closed, right? So what would that tell you?
If they're normally closed, so they're
overload protection. They're relays, right?
So they're
normally closed.
So that way,
you know, if they was to trip, they would become normally open. It would break the circuit, right?
So that's
why, like normally you're gonna.
Overloads are always going to be.
Right.
I mean, that's the whole point. Like they're closed until they're not, and then they open the circuit.
So I
just thought that was a good diagram to look at to like give you an idea of what those would look like.
And here's
another one. It gets a little bit more complicated, but what's this symbol right here?
Normally
open, right?
Normally closed.
And what is these? What are these right here? Overload relays.
No,
I mean, because all these symbols start going together. It's okay.
All right.
And now this is a little bit more complicated. We're not gonna
walk
all the way through this, but I was just wanting to show you like they do get more complicated
than what
you've seen. Electrical symbols.
They're used
to represent basic electrical and electronic devices that are used in the field.
They're
similar but may vary depending on voltage high or low.
So
normally it's like 600 volts.
If it's
higher than 600 volts, they look different, and 600 volts or less, they look different. So like,
I know
I put all these up here, but
y'all can go
back to this slideshow because I'm going to put a quiz on Canvas,
and it's just
going to be basically it's an open book quiz, but
I would
like for you to know what they are without even having to look them up. That way,
even if you
don't see them again for 3 years, it's like okay, cool, I remember that. You know.
Kind of
gives you an idea of what you're going to see. So see, this is a circuit breaker 600 volts or less.
And that's a
circuit breaker 600 volts or higher or greater. Well, greater than 600 volts, sorry.
So greater
than 600 volts. So it's a little bit different.
And then there's
your generator. We said that looked like a balloon, remember?
And then there's
an inverter.
A
contactor, which would be normally open. DC motor drive.
A
disconnect.
A draw
out circuit breaker greater than 600 volts.
A
fuse greater than 600 volts.
And see how
your fuse looks like. It's kind of more blocky 600 volts or less, but it's just like a little squiggle on greater than 600 volts.
Lightning
arrestor, draw out circuit breaker 600 volts or less. A motor is an upside down balloon.
You got your
overload.
Your
rectifier, variable transformer. Remember what we said? Those are like two upside down umbrellas, one on top of each other. Variable transformer, alternate symbol. See, there's alternate symbols, so that's what kind of gets confusing. Transformer, alternate symbol.
I guess that's
a balloon on top of a balloon.
And
so these were some videos that I had put up here. Let it load.
Once again,
like
this is just
like for reference.
So like I was
going to show you all this YouTube channel.
Like it shows
you all kinds of stuff. Like it even goes down to like electrical transformers basics. Let's see.
Motor control
indicator lights, start stop switch.
It's just a
good thing. Like if you're really wanting to get into it and you don't understand something,
like it'll
describe it to you in a way like even I can remember it after 5 years like of not touching this stuff.
So
just
I would write
that down, guys. Like HDL Tech Electric is a good
YouTube
channel to look at.
All right.
So that's basically all I was going to talk about, just like giving you a gist of the symbols and stuff.
Does
Does anybody have a book for motor controls? No.
Okay, cool.
Okay, cool.
So I'm gonna
be looking in chapter 5 control logic,
and this
is just kind of going over. Let's see. Robbie said I could show these symbols
on
on the computer, but I'm not exactly sure how to do that with my phone.
Because
he said I could show these over
the
slideshow,
like in a
slideshow. Let's see. I don't know.
Because
there's a lot of good.
There's a lot of
good ladder diagrams and stuff in here.
I'll just let
y'all look at it in my book, like whenever we get through talking.
Because there's a
lot of them you can look at and like try to follow. Let's see.
All right,
so we need to touch on a little bit about troubleshooting.
So
like troubleshooting.
What would you
describe troubleshooting as, Caden?
Right.
I mean, like that's how you.
Process to come.
Right. Yeah. So
I mean, it's like you basically use troubleshooting to figure out what's wrong with your system
to make it work.
again. So like,
if it was like an
overload trip,
like you
would know that there was like
something
wrong, obviously. So you'd have to trace it back and see what made that relay trip, right?
So
there's different methods of troubleshooting, and that's why I kind of was wanting to show y'all the book, because there's like a tie-down troubleshooting method
is a
testing method in which one probe is connected to either the L2 or L1 of a circuit,
and the
other probe is moved along a section of the circuit to be tested. So it's basically,
just
working your way down till you figure out like the spot that's
People do that, I call them poppers.
Poppers.
They'll just like start doing them on the.
Yeah.
And
then
let's see. All right. So
then
there's
you can troubleshoot open circuits, and an open circuit
is an
electrical circuit that has an incomplete path that prevents current flow.
So
and then you can troubleshoot.
Let's see.
Yeah, Robbie, how can I show them off my phone, like
these
ladder diagrams in the book? Is there an app I can get on my phone to show this, or
like can
I show them with this camera,
or what?
You could try to show with that camera. I'll figure out a good system.
Okay. Because I was wanting to show them some of these like diagrams in here.
Do you have an iPhone?
Yes.
All right. So what I'll do is I'll get air server on yours, and just like I do with the iPad, like you'll be able to
Draw on it.
Okay. Well, yeah. Let me change one thing on your computer real quick. Okay. We get a little bit of an echo. That's the problem is.
You're good.
Check. That should do it.
Because there's a lot of good diagrams in here that I wish they could see, but they don't have their books, so.
Do y'all have books?
I do have a book.
Okay, so kind of shoot them a few pages to double check.
Okay.
And
well, chapter 5 is not that long. Like chapter 5 is just about control logic, so they really could just like read over chapter 5. I mean, not even read over it, but just look at the diagram.
Make sure to
look at the diagrams and
yeah.
follow them out and try to understand what's going on in the diagram.
All right, so we'll put those pages up. But if you have PLCs that look just like that, because PLCs are made to replace relay logic. which is what we do in motor controls. We're kind of going backwards a little bit because PLCs are cheap now. But this is how we used to have to do it for everything. Okay, so we're going to reuse a lot of the same schematic symbols and such. Okay. Sorry
All right.
about that.
No. I was just wondering how to do it. So we'll figure that out later.
Like I'll get you a good system to do that.
All right. Thank you. All right. Sorry, guys. So, and also in chapter 5, I might assign y'all like chapter 5 to do. Has anybody, you've purchased the book. Has anybody else purchased the book? You have? Have you, Dylan? Have you purchased the book? All right. So, because I kind of want y'all to answer some of these questions. But I mean, they're relevant to what you would be doing. Like, it's not just busy work. Like, it'd be relevant to how you would troubleshoot. Like, troubleshoot's a big deal. And really, that's the only thing I would want y'all to answer. Is about the 5-5 checkpoint. And that would just be 1, 2, 3, 4 questions. And if y'all want to do that in class, like, because do both of y'all have hydraulics too? Okay, but if you want to do it like on one of your lab days, you can just answer these 4 questions. It's not going to take you long. But you know how to troubleshoot, but it's just a refresher. So, all right, so I'm going to assign that. So, Brianna, and Samuel, since y'all have the book, it's going to be like chapter 5, 1 through 4, and that's on page 193. And I'll put that in I'm dyslexic, 139. And that's just 1 through 4. And I'm going to put that on Canvas as well, and it won't be due until like next Sunday or something. So, all right, now let's move on. All right, so is everybody good on the basics of symbols and diagrams? We all understand it. We get what they're used for. Cool. Okay. Transformers. We're going to dive deep into transformers. Alrighty. So, talking about transformers, let me get to the page I was on here. Transformers are chapter 15 in the book. For anybody that has the book that wants to read in there. I know I have it marked. I'm sorry, guys. I'm kind of going crazy right now. Dude. I got so many pages turned down. I think that it's chapter 15. Nope, sorry. Chapter 11. Okay. So, history of the transformer. Just doing some research on the transformer. It was invented towards the end of the 19th century, and it allows power stations to be located miles away from their actual load. Before that, there were DC systems with the power supply close to the point of load. So now, we have substations with transformers in them, instead of like a local Walmart having to have like a huge power station right next to it. So back in the day, if it was like a big building, they would have to have a DC power source right next to the building or very close. So transformers made it more efficient for, power companies to just have substations instead. So, and the power industry discovered that transformers were much more practical, and their definition of transformers are devices that take the high current - relatively low voltage output of an electrical generator and transforms that to a voltage level that can be transmitted in a practical way to consumers. All right, so let's see. And this is literally straight out of the book. So I took both of those definitions to try to compare. A transformer is an electric device that uses electromagnetism to change voltage from one level to another, or to isolate one voltage from the other. So there's 2 types of transformers. Does anybody know what those are? No?
One was primary?
No, we're about to get to that. There are 2 types of transformers, is step up or step down transformers. So like you're going to take it and step up the voltage, or you're going to step down the voltage. Cool? We understand how that works. Okay. So what does a transformer consist of? This is where you was talking about 2 windings. So a transformer usually consists of a pair of windings, which is called primary and secondary, linked by a magnetic circuit or core. The primary winding is the coil that draws power from the source, And the secondary winding is the coil that delivers the energy at the transformed or changed voltage to the load.
Is one longer than the other?
It just depends. It depends on the turns ratio. So, like, your primary winding is what's taking all that energy from the source, like whatever power source. So, like, take, for example, like on this next slide, I think. Okay, cool. So, you see those on the power lines all the time, right? And those are just transformers. And they step down the voltage from the line to the distribution system, so that way, like, we can use them in our houses and everything. So, like, they're taking that high voltage and stepping it down normally to, like, 240. And then, like, to our power outlets, it goes to 120. So, but distribution transformers perform the last voltage transformation in a distribution grid. So, they're pushing all that voltage down the line until they get to those transformers, and then they transform that into voltage we can use in our homes, our shops, whatever. Okay, and this is an industrial transformer, a transmission transformer, and they work with much higher voltage in industrial settings. So that's what you would more likely see in a substation. Like, you drive by these when you're driving down the road, right? Have y'all ever noticed this in a substation? That's working with, you know, much higher voltage than those little transformers on the line. But that's also a step-down transformer because that's stepping it down from the transmission lines to the distribution lines. So you kind of see what's happening here. Like, it's basically just a checkpoint for the voltage, like saying, hey, you need to slow your roll. Like, we got to have less voltage. Boom, stepping it down to this line. All right. So let's see here. All right. Now, I don't think I added a slide for this. All right. When alternating voltage is applied to one of those windings, generally the primary, a current will flow which sets up an alternating flux in the core. The flux links both windings, which induces an electromagnetic field in each of them. Electromagnetic field. And that's what gets the transformer turning. So, let's see. I need to go over turns ratio with y'all. Yeah, because we're already on the summary page. I didn't really do a lot of slides for the transformer, so I'm sorry about that. But, okay, so let's just talk about it. So, the turns ratio is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding of a transformer. So, basically, if there's twice as many turns on the secondary, twice the voltage is induced on the secondary. So, let's see. I'm going to try to show it on this camera because it's kind of hard to talk about it if you don't have a book and you can't see it for yourself. Let's see. Transformer transfers AC energy from one circuit to another. Alright. I don't know how to do this, guys. I don't know if you're even going to be able to see this or not. Can you even see this? Not really, can you? No. Crap. Well, whoever's watching this live stream, I'm so sorry. I knew this was going to be an awful thing. For me, anyway. Alright. Let's see. Ratio of primary to secondary is 1 to 2. Alright, so if like the ratio of primary to secondary is 1 to 2, what kind of transformer do you think that is? If it's like 1 to 2 ratio, so like step up, right? So because like it's 1 on the primary, 2 on the secondary, so it makes it a step up transformer. And what does that do to the voltage if it steps it up? A 1 to 2. 1 to 2. It increases, but it doubles, right? From 1 to 2. So it's doubling the voltage in a step up transformer.
So are those usually the like bigger ones?
I mean,
Because I know we got like decent little sized ones in the plant I work at.
I
was wondering if those were step up.
Well, like, it doesn't necessarily mean anything from like the size, I don't think. Like, of course, if it's like dealing with higher voltage, that basically means like the size. It doesn't matter if it's stepping down 10,000 volts to whatever voltage. Like, the bigger they are, the more voltage like they're dealing with. So that's why, like, you see those little transformers on the power lines, they're not that big because they're not dealing with but like 480, right? But you're working in a plant, they're like 4180, or, you know, literally sometimes thousands of volts. That's why they're so much bigger.
Usually I see them around the panels where the crane operation is.
Right. All right. And then let's see. I'm not gonna make y'all learn about that. Let me had some notes too, because it was something about, let's see. Alright. So, one thing to know is transformers are not creating or destroying energy. Like, so transformers have to have a power supply. So, like, a transformer is not making or destroying energy. So, like, you would need some type of power supply, a generator, a motor, whatever, for a transformer. And Robbie wanted me to clarify that almost everything is a transformer in itself. So, like, a motor isn't actually a transformer. That's where it kind of gets confusing for me, too, because I'm like, okay, but we have a transformer, you know, with a motor.
Kind of like how a contactor's a relay.
Yeah, it just starts getting confusing when you dive that deep into it. But the gist of it is everything is a transformer. It's transforming something into something else. So that's what he wanted me to kind of like clarify too. Is only one part, amperage is the other. So like voltage is only one part of a transformer, amperage is the other. And how you can figure out power for a transformer is, Robbie said to remember, as easy as pi. So where we have Ohm's law, pi equals, so it's P equals IE. So it would be P over IE. So power over current over voltage. So that's how you would configure any type of, like, if you was trying to figure out what a 100 turn to a 1 turn ratio transformer would be. Like, you can input like how much voltage and how much current, and you can figure out how much power it would have. So just remember, like, easy as pi is something you can convert those. So let's see, what else do I have in my notes here? All right, and eventually we need to get into just doing a couple of problems with like turn ratios, like that way you can figure it out for yourself. All right, so let's talk about like losses, so transformer losses. All right, transformers are super efficient, but they're not perfect, so anything man-made is never going to be perfect, right? So there's always going to be some type of loss, some type of resistance. There's never going to be a perfect world in any shape, form, or fashion. So, let's see. Not all the energy is delivered to the primary side by the source. The majority of anything that you lose in the electrical world is like through what? Heat, right? You lose a lot of your energy through heat. So that goes for transformers as well. So there's 3 types of losses. Does anybody know what those might be? So there's going to be resistive, which is, that's pretty common in electrical, right? Like you're going to lose a lot to resistance. Eddy current, and I don't even know how to say this, but hysteresis losses. All these losses make the typical iron core transformer hot when operating under full load. So that means they're going to lose through the heat, like I said. Resistive losses obviously just come from the resistance of the coil winding. So any type of inductor is going to have some type of resistance. So we all understand that it's going to have some resistive loss. Now getting into eddy current. Because iron is a fair conductor of electricity, the varying magnetic field that induces a voltage in the secondary of a transformer also induces small voltages in the iron core of the transformer. These small voltages produce eddy currents, which in turn produce heat. This heat also represents a loss because it does no useful work. So eddy currents are minimized either by making the core out of thin sheets that are insulated from each other, or by using powdered iron cores instead of solid blocks of iron. The insulation between the laminations of a laminated core breaks up the current paths within the core and reduces the eddy currents. This is the same technique used to reduce eddy currents in solenoids. So that's why the cores are laminated, to reduce eddy currents. And that's like a question I had in the summary. So, and the hysteresis losses results in heating of the iron core as well. So basically everything we're reading about losses is just due to heat. And let's go over the summary while we're sitting here. What are the 2 windings of a transformer called? Primary and secondary. Wire transformer core is laminated to reduce the eddy current that has arisen from the induced voltages through the core. This reduces the heat loss of the entire core. And why do control transformers usually have two primary coils? So control transformers have two primary coils. And primary coils of a control transformer are crossed so that metal links can be used to connect the primaries for either 240 or 480 operation. So I'm about to show y'all. Let me just pull this up because I know it's kind of hard for me to like just read to y'all and you not be able to see stuff. So that's why I wish I could show you the book. Can be used to connect the primaries for either 240 or 480 operation. Let's see here. Control transformer schematic. That's what we're going to look up. Control transformer schematic. Alright, and I'll show you what it's talking about here. Alright, cool. So, you see how they're crossed? That's the two primary coils, right? And so, if you wanted to bring it down from, if you wanted to bring that voltage down to 120 from a line voltage of 240, you would need to connect your coils in parallel. And how you would do that is so you would take H1 to H3 and H2 to H4. So that, no, wait, I said that wrong.
H4 to H3 and H2 to H1.
Hang on, the book's different than what I saw. Look at this one down here. So, no, I said it right. So if you wanted it in parallel, you would connect the two outer ones. So whichever one this is labeled. On that transformer there, it's labeled H1, H2, H3, H4. But looking at this schematic, you would do H1 to H3 and H2 to H4. So you'd want it in parallel if you were stepping it down from 240 to 120. But now, if you were stepping it down from 480 to 120, you would need it in series. So how do you think you would get that transformer in series? You would just have you would have a metal link right there between those two, right? So that would make that one big primary coil instead of having two separate. You get that? Okay. Tell me if I'm confusing you because sometimes I don't explain stuff well.
Usually by the time you get done explaining it, it makes sense.
Yeah, I just go around the world to say it and I'm sorry. So, anyways. Alright, so a control transformer is a transformer that is used to step down the voltage to the control circuit of a system or machine. The most common control transformers have two primary coils and one secondary coil. The primary coils of control transformer are crossed, like how you see in here. They're crossed because normally it just looks like waves, right? Like there's nothing going on right here. It's just a bigger coil to a smaller coil if it's a step down, or a smaller coil to a bigger coil to a step up, right? Okay. So the primary coils of a control transformer are crossed so that metal links can be used to connect the primaries for either 240 or 480 operation. In most applications, a control transformer is used to reduce the main or line voltage of 240 or 480 to a control voltage of 120. So that's what I was telling you. Like, so if you're going to step it down from 240, what does it need to be in? Parallel? Okay, cool. And if you're going to step it down from 480 to 120?
In series.
Cool. Y'all all understand that, right? And you understand why? Do you understand why that's happening? Okay, so if the primary coils are connected in parallel, the effective terms of the two primary coils is 200. The same as if there was one primary coil. If the secondary has 100 turns, the turns ratio is 2 to 1. This means that an input voltage of 240 produces an output voltage of 120. So that means that it's just it's 2 to 1 if it's in parallel. You've got two separate coils to one coil on your secondary. Do you understand how that's working now? So 2 to 1, and that's a what kind of transformer? Step up or step down?
Step up.
No,
Step down.
Step down. So you're going from 2 to 1. It's a step down, correct? Right? Caden, are you getting this? Okay. So a turns ratio, whatever number is in front, determines if it's a step up or a step down? So if it's a 1 to 2, what would it be? Step up. Cool. Now are we getting it? Kind of clicking? Okay, cool. So, and the reason that you need them in parallel, if you're coming from 240 to 120, what is 240 divided by 2?
120.
Okay, cool. All right. Now, if we need it in series, to obtain a control voltage of 120 from a line of 480, the two primary coils must be connected in series. If the primary coils are connected in series, the effective terms of the primary coils is 400, making the turns ratio 4 to 1. So that's also a step-down transformer, but this means an input voltage of 480 produces an input voltage of 120. So let's just see, let me just work it out right here. So we got 240 divided by 2 is 120, right? 480 divided by 4 is 120. So you're basically just dividing by that turns ratio. You see how it's working out? Like, because it's 4 to 1. So you're stepping it down. It's 4 times as much as your secondary. Am I confusing you? Everybody gets that now? Kind of clicking? Okay. Robbie just wanted me to show y'all that example because that's what we're going to be working on this week. We're going to be working on one of those transformers right there. But we're going to take it to the shop and you're going to have a power supply and you're going to wire that up. And you're going to see how it works in series and how it works in parallel. So, let's see here. All right. So, basically in your lab this week, you're going to be converting 240 to 120 or 480 to 120, what we just talked about. And if you're confused, tell me, like it's not going to hurt my feelings because sometimes I don't explain stuff the right way. Does everybody get the turns ratio aspect of a transformer? We all get that. Okay. So if the number is bigger in the front, so if it was a 2 to 1 ratio transformer, what kind of transformer is that? 2 to 1. Step down. Right. Because you're going from 2 to 1. And if it was a 1 to 10 turns ratio, step up because you're stepping up from 1 turn ratio to 10 turn ratios, right? Okay. Now, let's see here. Let's see here. All right. Okay. Now let's see. Let me show you some examples of step-up transformers. Step-up transformer. Do y'all want to see one from 240 or 480? Let's look at that. Images.
Okay, that looks like the transformers that work.
The bigger ones. Let's see. Control transformer. So you have a 120 volt AC primary side, right? Because we're stepping up to 480.
That's got 4 wires, right?
Yeah, it's a 1 to 4 ratio, turns ratio. So, let's see what this one, primary voltage 480, secondary voltage. So, what would we do if we wanted that transformer to be in parallel? Which ones would we connect on that bottom line, on those bottom coils?
Where X3 is that you connected to X2, and where X2 is that you connected to X3, right?
For parallel?
Yeah.
So for if we wanted that, if we wanted that transformer in parallel, we would connect X1 to X3, right? And X2 to X4. So we would go X1 to X3, X2 to X4. That way you would have 2 separate coils, right? But if we wanted it in series, all you would have to do is connect X3 to X2, and that makes it one big coil, right? Okay.
So you're like adding wires and...
Yeah, it's just a metal link. That's all it is. I mean,
I don't know.
Basically just like a jumper. You get what I'm saying? So
yeah, I get it. Just in my head, it was playing differently.
And once you put your hands on it, like Robbie is gonna help me come up with a lab because this is my first semester, so I don't want to steer y'all wrong or nothing. But he's gonna help me come up with a lab to help y'all understand this better than what the book does, because reading comprehension is not one of my strengths, and also sitting here listening to somebody is not one of my strengths either. But once you hear about it and you kind of got an idea of it, and then you put your eyes on it, you're going to be like, oh, that's not that hard, right?
So will he be here this week?
Probably. Yeah, I mean, he's already here. He's in his office.
Yeah, he was talking about how good he felt.
Yeah, he's talking about how he feels like a brand new man.
Like he's 25 again.
He also said don't talk bad about him, so he can hear us, is what he's saying. Yeah. Alright. So y'all just bear with me, because I'm still figuring out how to portray this information to you guys as well. But are y'all understanding so far what I'm trying to get to? Okay. And if I'm confusing the crap out of you or anything, just say, hey, stop, like you're confusing me, like we need to go over that in depth more, okay? Alright, so let's go to, y'all really need a book. Alright, so let's do troubleshooting transformers. Let's talk about that. So, after a transformer is installed in a circuit, it may operate without failure for a long time. One reason for this is that transformers have no moving parts. No moving parts. So, if a transformer does fail, it appears either as a short circuit or an open circuit in one of the coils. The two methods that can be used to determine whether a transformer has failed are to measure the input and output voltages and to check the transformer resistance. So, to measure the input and output voltages, if a transformer is connected in a circuit, the transformer can be tested by measuring the input and output voltages. The transformer is good, so the transformer is good if the input and output voltages are reasonably close to the theoretical values. So if the input and output voltages are close to what they're supposed to be, theoretically, because nothing's ever perfect, that transformer is still good. So something else is going on, right? Okay. The current levels are tested if the voltage does not stay constant. Although the initial voltage may appear normal, it may not hold up when the transformer is fully loaded. Let's see. So, and there's also a diagram in here how to test a transformer. And that would be something good to know, like if we're going to troubleshoot these transformers that we wire up. So that's kind of why it's good to have the book, I guess. But we're going to figure out next week how to show you these pictures in the book, so it's not going to be as like all over the place. Robbie's going to help me figure it out and I'm going to let y'all look in this book too, and we can take this book back there whenever we're wiring those transformers up, so that way we can be like, okay, if something doesn't work, or even if we want to just know how to troubleshoot a transformer, you know, you can use your voltmeter to do that. Alright, and checking transformer resistance. A DMM is set to measure resistance, can be used to check for open circuits in the coil, short circuits between the primary and secondary coils, or coils shorted to the coil without power applied to the transformer. So, open circuits in the coils. The resistance of each coil is checked with a DMM. This is basically just explaining how to do what's literally in this diagram, so I'm not going to read it all to you, okay? Cool with y'all? Cool. Alright. Alright. So, let's watch some videos. How about that? Are y'all like a video class? Like y'all like watching videos? Yeah. I like seeing stuff with my own two eyes. So, let's just look up let's say, how does a step up transformer work? There's got to be YouTube videos on here. Let's watch this 5-minute video.
It's hard to believe that Mint Mobile can be good at just $15 a month. So, as Mint's new owner...
Wow, no, me too.
Alright. Is this going to have any noise?
Transformers are composed of an iron core ring wrapped in coils. One coil is connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives a transformer its unique electricity altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil.
Okay, cool. Y'all get that? Okay.
In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil.
And you see how it literally shows you how there's more turns over here, so there's more coil wrapped around than there is on this side, right? Okay.
The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary.
So like, since there's less windings, obviously,
Mm-hmm.
the other side of, step up or step down.
Mm-hmm.
Is that like saying that there's less ions going to be pumped through it or something?
So, like, that's normally, like, you're looking at, like, copper or, like, anything inductive, but, like,
Yeah.
so, yeah, what you're saying is, like, you're talking about, like, the electrons or whatever. Like, I don't know Robbie, come here and answer this question. Because this is, like, more like something like Robbie would be able to tell you about. He's all about electrons and conductivity and all kinds of stuff. Ask him.
I didn't mean you to have to call me.
No, it's okay. I mean, he's an electron guru. Answer this question for Dylan. So, ask him your question.
No. If you know the question, it'll sound better coming from me.
So what he's asking is like, basically how this has 20 turns and, this has less turns over here.
Mm-hmm.
So is this side producing more, you said ions, but you meant like electrons,
Yeah.
right? He's asking about the electrons of like the conductivity of like the electromagnetic field and stuff.
Okay, so the easiest way to think about this is every length of wire is going to have a certain amount of resistance.
Right.
Okay, so if that has less wire, it has less resistance, right? So what's going to happen is, let's say that's a 20 to, let's say a 10, okay?
Mm-hmm.
That means that it's going to have half the resistance, which is going to do what to the current? Less
Ohm's
resistance.
law.
It's going to double the current, right?
Right.
But at what it spins. All right, so if we have 20 turns over here, that meant that voltage dropped that amount of voltage over 20. So now if we're dropping voltage over 10, we're only dropping half the voltage, okay? So in this particular thing, we've got to step down. So what it's going to do is it's going to step down the voltage and it's going to step up the current by the same proportion, okay? We call them step up and step down based off of just voltage, but they're doing the opposite thing to the other, like to current, okay? So if they step down by half, they step the current up by double, okay?
So when you use a transformer, your current's going to go up.
Well, in a step down it would, but in a step up, like if we had a transformer that we wanted to take like 1,000 volts,
Right. Your current would
have
go
to come
down.
from somewhere, because the power that you're putting in, we're not going to create nor destroy power, and power is current and voltage. So if we step one up, we're going to have to step one down by the same factor.
Okay, I think I agree.
All good?
Okay. I just didn't want to steer him
No.
wrong with the electron question.
Oh, y'all are good.
Okay.
Y'all good.
All right. So, any more questions before I press start again? And you understand what I was talking about with the Ohm's law thing, because like you're in DC and AC,
And whenever he really explained that,
right? It clicked in your head
yeah,
now.
I've taken DC and AC.
Yeah. So it's like if one goes up, the other must come down. Yeah. All right.
Coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio.
Maybe. This would be one good for us to do together, okay? Does anybody have their notebooks with them? No? Okay.
I got 8 notebooks beside me.
Well, why don't you write in that notebook, you and Caden both? Alright.
Okay, I got a crayon and a pen.
Alright. So, just so we can start wrapping our heads around this. Alright, so the formula is your voltage of your secondary, which we don't know what it is, over the voltage of your primary. So that's going to be 120 volts. So it's going to be V over 120 volts. And then it's going to be your turns over your secondary. So 10 over the turns of your primary, 20.
Secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120 V. This results in a calculated step-down voltage of 60 volts.
All right. So let's see here. So all they literally did is they isolated that V or whatever. Y'all know how to do math. Duh.
I don't know if I do or not.
Well, you're going to bring that 120 volts over and multiply it by that 10 divided by 20. All right. Did you do that step? So it's going to look like this. Can you see that? So it's going to be 10 over 20 times 120 volts. And then the easier thing to do is just go ahead and divide 10 by 20, right? So what is 10 divided by 20? And they've already told us, but let's just do it anyways. 10 divided by 20 is 0.5. So now, whatever value you get of 0.5 times 120 is going to be the voltage that you're getting out of that transformer, in that step-down transformer. So that's how you figure out what voltage you're going to be getting out of any step-down transformer. So let's do another one just so we know what we're talking about. So the formula is the voltage of your secondary over the voltage of your primary, and the turns ratio of your secondary over the turns ratio of your primary, right? That is our formula. All right, so let's say that we have, I need to do this on the board probably. Robbie, can I turn this camera towards the board? Robbie. All right. Yeah, let's do that.
Oh, cool.
A little board.
Oh, man.
Yeah, that's what I need. Okay. Thank you.
Need them harder.
Yes, please. Please, please, please.
There's 3 of them in the floor right there.
Sammy, you didn't have to call us out like that.
Now that I'm not dying,
Thank you, Samuel. All right.
We're glad you're not dying, Robbie.
Okay. Y'all,
yeah.
this is like such a great setup I've got going on right here. Dude, how can I show my board and me and everything else going on?
Didn't you have like 2 cameras?
Yeah, but like,
Did something happen?
one of the issues was the amount of data trying to get out was
All right.
Crashing?
one of the issues.
And this is going to be upside down, I feel like, right?
Well, like, probably do it and then turn.
Okay.
How about you ride on it and turn it?
Yeah, that I'm trying to even like figure out how to show it bigger, maybe. I need to point. I'm literally like having a lot of issues.
What we'll do is we'll turn it this way.
Yeah, now find the board. Okay. All right, cool. So let's see. Yeah, okay, now we're the right way. All right, thanks, guys. Sorry.
Nope.
Still figuring all this out.
I bet
All
that
right.
changed your life.
Yes. So, yeah, now I can actually draw and talk to you guys instead of just like, do you know what I'm talking about? Duh. Alrighty, guys. Alright, so this is our formula. V of our secondary, which is just voltage, over V of our primary.
What's that?
I haven't made it up yet. Okay. And so turns ratio of our secondary. Sorry, I know my handwriting's really god-awful. Over turn ratio of our primary. Alright, so now let's just say we have a transformer. That's a beautiful transformer, isn't it? And we have another side. Boy, look at that. I should have been an artist, shouldn't
Oh my gosh, yes.
I? Okay.
Luckily, we can't really see it.
Okay. Alright, so now, you can't see it?
Nah, we're missing the bottom.
Now you can see it?
Yeah.
Alright, so we have 120 volts, and let's just say we have a 40 turn, and we're going to do this is a step down. So, step down. Dude, yeah, this is like the best thing like ever.
So it would be like a 20 turn?
Hang on, Dylan.
I don't know, I'm getting really excited.
Hey, there we go. Hold on. Y'all can see it a little bit better now?
Yeah.
Okay. I'm sorry, I know this is
The
crazy.
whole thing and that drawing
Yes.
is just blended.
Yes. Okay. So we got 120 volt, 40 turn. Let's do a 40 to a 10 turn. How about that? So this is a step down transformer because we're going from 40 turns to 10 turns, right? So now we need to know our voltage. So we don't know the secondary voltage yet, so we're just going to put V over voltage of our primary, 120. You know what? Yeah, that's what we're going to do. Okay. And then turns of our secondary, so we got 10 turns over 40 turns, right?
Mm-hmm.
So now we need to isolate this. So we're going to move our 120 over here and we're going to times it. I know you can't see that, but that's what we did. All right. This is like the worst setup ever, isn't it? Okay, now you can see that. So we've got 10 over 40 times 120, and we're trying to find our V. All right, so what is 10 divided by 40? Somebody do it on their phone calculator.
0.25.
0.25? All right, so 0.25 times 120. Do that. So what is 0.25 times 120?
30.
All right. So that's going to be our voltage coming out of it, right? 30. So now we have a 120 volt 40 turn transformer stepping down to a 10 turn transformer that's going to produce 30 volts. So is it kind of helping that you can like see how you can do the equations and figure it out for yourself? All right, so let's just remember that it's secondary voltage over primary voltage, secondary turns ratio over primary turns ratio. All right, let's keep watching this.
Thanks to you, I learned how to do fractions today.
Wow. Awesome, man.
In this animation, we'll look at how a transformer works.
Wow, he's Australian.
This is a typical oil-cooled step-down transformer. Transformers step voltages up or down. Electricity comes in on one side at one voltage and goes out on the other at a different voltage. On the outside of the transformer are a number of external components. Some help it to remain at a good working temperature, some help make it safer in the event of an accident, and some are used for monitoring. The radiator fins help cool the oil in the case. The conservator tank allows for the oil to expand and contract as it heats and cools. The explosion vent protects the transformer in the event of a major fault. The bushings insulate the conductors where they enter the case. The tap changer sets the exact amount of voltage change. The Buchholz relay lets us detect the presence of gas caused by the deterioration of the oil and/or a rapid increase of oil pressure. Let's look inside the case at the transformer itself. Within each transformer case are 3 actual voltage transformers, one for each phase. Each has its own conductor in and conductor out. A transformer is a laminated steel core surrounded by 2 different layers of wire windings. One set of windings has fewer loops of wire than the other. The one with fewer loops is the low voltage set of windings. The low voltage windings sit between the core and the high voltage windings. Let's see how it works. The current comes into the transformer through a conductor that joins onto the high voltage windings. This induces a magnetic flux in the iron core. This flux induces a current in the low voltage windings. Because there are fewer complete loops of wire in the second set of windings, the current sent out from them has a lower voltage than the one that came in. To adjust the final voltage further, we can use tap changers. These reduce the number of windings on the low voltage side still further, by changing the location of the conductor that leads out of the transformer. Notice how the sine wave reduces as the tap changer connects to fewer windings, reducing the voltage.
So like when I worked for Southern Power, we had load tap changers at like our wind sites and everything. And, you know, if we needed to produce less voltage, like those would close in, like, and I never really knew what they was for until I started like just looking into them and everything. So you might see those if you like get into like the power industry, they'll have load tap changers on the transformers. And that's basically just if you need less voltage. Stepped up by a transformer on the current signal. Alright, let's see here. Alright, so we just went over the step down formula. Now,
Won't the step up formula be pretty close to the same?
that's what I'm looking at here. Let's see here. It gets kind of, you can get deep into all these formulas and stuff. I mean, I'm not going to make you remember all these formulas because I can't even remember all these formulas. But
Well, if you did the same formula that you did on the step down for the step up, if you put 40 on the top, 10 on the bottom, that'd be 4 times 120.
hang on. I don't know. It's talking about a power differential. Alright. So we just went over step down. Right? Or did we just went over step up? Oh, we went over step up and step down. Videos. Caden, you already getting tired on me?
Yeah.
Did you work today?
No, I slept in.
You slept late?
Yeah. Aww. You slept. Finally.
I mean, the voltage is too low to run a microwave.
Primary, secondary. I just need the formula. want that formula. I wonder if it's got it in the actual textbook that I keep preaching at y'all to look at.
Yeah, that you can show us.
Yeah, but you couldn't even see it if I showed it to you.
Yeah, but we can go back to the video and zoom in.
Step. Step down control 250. I know y'all are like so intrigued by me right now. It'll be better when we get in the lab, I promise.
I'm ready for the lab.
Let's see.
I'm gonna come here all 3 days, but I'm so excited about it.
I bet you are.
Now I'm gonna do it every single day I come.
I bet you are.
One day at a time.
It's connected to the same.
No, I'm gonna do the whole lab and come back to it.
This book lied to me. It lied. Okay. Turns ratio. Alright. For example. Transformer ratios.
Let's go on the Khan Academy. Let's go on the Khan Academy. No.
Khan Academy. Transformer connections. Hey Rob, one more question for you. So like, oh son of a gun, sorry. On the step down formula that we just practiced it is secondary voltage divided by primary voltage and secondary turns divided by primary turns. What is the step up voltage? Do you know? I mean the step up formula.
Well, it's just gonna be flipped. Like,
okay, so that's like what you was just. That's just like you was just saying.
Like a, you know, it'd be like 0.4. You know, so anything you put in is 0.4 of whatever, and then the other way around would be like a 1.2 or something, right?
Right. Okay.
Cool.
That's what Dylan was asking. And then another thing too, the easiest pi thing. You never went over that with me, so.
Okay, so it's just power or volt amps.
Right.
Equals current times voltage.
Right.
Okay.
Volt amps
So
is the same as watts, right?
Yes.
That's what's confusing me in the book because it's.
When you're dealing with alternating current, we use volt amps to differentiate it from pure wattage, which is a heat dissipation, which means that all the energy you put into it gets dissipated. Like when you're dealing with an inductive load, some of that power comes back to you reflected. So we differentiate the two types of power as wattage when it's a purely resistive or DC circuit, and volt amps whenever.
Okay.
So in here you're going to deal with volt amps.
All right. Okay. Yep. All right. I'm just gonna let's see step down transformer. So let's just summarize what we've learned today. How about that?
That sounds good.
All right, because I don't want to overload y'all too much, and I don't want to like get off on a rabbit hole and confuse myself and everybody else. All right, so what we've learned today is, let's see. So the step down formula. We've also learned that I can't write. All right. So just to summarize, the step down formula is, does everybody remember the step down formula?
Yeah.
So it's going to be secondary voltage over primary voltage, right? Turn ratio over primary turn ratio, right? So if you have any of these three things, you can find the other just by doing math. Okay, cool. And then what is a transformer primarily consisted of? The two things. They're called windings, and it's primary and secondary, right? So you have primary winding and you have secondary. And what does your primary winding, what is its job? Right, so it takes whatever the power source is, and it's then the secondary converts that or transforms that into whatever it's pulling needs. So like if an outlet needs 120, there's transformers and like it blew my mind that Robbie was telling me there's transformers in like our little phone chargers. Like it might take that 120 and step it down to like if our phone only needs 24 volts. That's cool, right? I mean, I didn't ever think of it like that.
Until I started hearing.
So.
I bought one and it was humming.
Yeah.
Then I took it apart.
So. Y'all can see this like so good, I can tell already.
Well, my fiance said, it's humming, I don't want it in the house. I'm like, well, shoot, I'll take it apart then.
All right. Cool. So the primary takes the power from the energy source, right? Energy from the power source. Okay. And the secondary transforms that. So that's literally why it's called a transformer, right? All right. And what else did we talk about? So like turns ratio is how you can figure out what voltage you're getting out on the other side, or how you can figure out if a transformer is what two types of transformers are there?
Step up and step down.
Right, so there's step up and step down. So the turns ratio, if it was 2 to 1, that is a what kind of transformer?
Step down.
Step down, correct. And if it was a 1 to 4, it is a
Step up.
Cool, we got that. We've got that concept. All right, and now the last main thing you need to know, especially for your lab, is, let's see here. Ooh, sorry, microphone. No, not the fractions. All right.
Like the only thing I fell on to is
Right, so if we have a 240 volt primary. Cool. Okay, so let me just draw this out so you can see it just a little bit. Can you see this? Okay, just making sure. All right. And we have a coil here, and it's a beautiful coil. And then this beautiful coil crosses to come over here. And then we have another beautiful, beautiful coil. And it crosses. And then let's see, let's just go ahead and draw in our circuit. Wow, look at that. That's a circuit, guys. Okay. Okay, and then we have just a regular little 100 turns coil over here. We've got a power source, and then it comes back around. I know my drawing is like the best ever.
I'm impressed.
Yes, I know you are, Dylan. Alright, so if we're wanting to convert 240 volts to 120 volts, what did I tell y'all it needed to be in?
Parallel.
Ha! Dylan was listening. So how would we connect this in parallel? Hang on. Let me just go ahead and draw this out. So we got 1, 2, 3, and 4. How would you connect that in parallel?
You need a little jumper, wouldn't you?
Dylan, what number would I connect to what?
Oh, you need to connect that 1 to 3.
What are you doing, boy?
I don't know.
We need it in parallel. So where does 1 need to go?
Oh, 2.
Okay. So we need it in parallel. It needs to go, 1 needs to go to 2. And 3 needs to go to 4, right?
Correct.
So now what ratio is this? You've got 2
2 to 1.
to 1. Cool. And we understand that that is doubling. Well, reverse doubling. So 240 divided by 2 is 120. We get that, right? Okay. Okay. I can see that you get it. I can see it all in Caden's face that he gets it. All right.
My mom always said I was a real good trier.
Yeah.
Wasn't good at nothing, but at least I tried.
480. All right. So now I'm going to draw another pretty little schematic here. And we've got da-da-da-da-da-da-da, da-da-da-da-da-da, and then it crosses, boom, 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 boom. And then we're just going to step it back down. Da-da-da-da-da-da. Cool. That's a beautiful transform. All right, so now we've got 1, 2, 3, 4. Now, if we want it to go from 480 to 120 volts, series. Now, how do you connect it in series?
Oh, I know this one now.
What is it?
Is it 1 and 3?
1 and 3?
Yeah.
You're wrong. It's 2 and 3.
Works.
All right, 2 and 3. So that would mean you just have one big coil. And so that would be 480 to 120. All right. So that pretty much sums that up. And so in the electrical world, how do we lose stuff the most? Like, how do we lose energy? Heat, right? So we lose it through heat. And what are the 3 type of losses, even though I can't, the hyper something something. Hang on, I'll tell you exactly what it is. So, let's see. Hey, there we go. It is hysteresis. All right, now what was the other ones? Resistive. But you was close. And what's the other one that was like a name? Eddy current. Eddy current losses. And because of eddy current, what do we have to do to the core? Remember what I said? It's laminated to help reduce eddy current, right? So if that's like every question on the test, the reason that the core is laminated is to reduce eddy current, right? Okay. And let's see. I'm just trying to make sure we go everything. So talking about our lab for this week, we're gonna wire up that transformer to step down from 240 to 120, and then we're gonna do 480 to 120. So that way you can put your eyes on it and understand kind of what's happening. But do y'all understand the gist of transformers? Like, do y'all get what transformers are doing and why they're a thing? I don't even know how to fix this camera, so I'm upside down. Cool. I mean, whatever. But you understand transformers, right? All right. And what was here's another quiz for y'all. What was the YouTube channel that I told you was a good reference? HGL Tech Electric. So if you ever want to dive deeper into that kind of stuff.
I'm subscribed now.
Good. So subscribe. Seriously, like, it's a cool channel to watch because it'll basically anything you can think of, it's on there.
And
so
this is not a endorsed class.
No, I'm not sponsored by those people at all. I wish I was. But they only have 2.4K subscribers, so I don't think that, they would have any money to sponsor me anyways. But that's basically all I've got, guys. I'm gonna stop streaming